the last part of the course. I wanted to do some more on optics today because, again, some of you are going to be taking a lab, and I wanted to prepare you a little bit better, if I can, for that. So I changed my notes on the ray optics because I wanted to show you a couple of demos that were not in that original PowerPoint setup. I'll send you a revised version tomorrow. There's yet some more revisions I want to make, namely to add something about the vision of how the eye works. I think that's very important that you understand. Yeah, that's a good subject. Fascinating, actually. So, but I wanted to go back over some things here. We'll view this. Where are we? No, I want to go back to here. Yes. Okay. So we didn't do this very thoroughly, but I think some of the things are very interesting and simple, namely the incident and reflected ray, and the law of reflection, which says that if you judge things from the normal to a surface, the angle between the incident beam and the outgoing beam with respect to the normal are equal in the case of reflection. That's pretty obvious. Bounces this way, bounces out that way. What's more complicated is when the light travels into the material, comes in. The easy part is it bounces off at the same angle. Theta 1 prime is equal to theta 1. What's more complicated is the fact that it bends toward the normal if it goes into a more dense material, and it's given by Snell's law. Quickly going over this one more time. What stays constant when that light, any electromagnetic radiation, enters a new, denser medium and slows down, the factor that changes when the speed changes is the wavelength. In other words, the fellows who go into the slower medium, they go at the same timing, but the fellows going faster catch up with them, and so their wavelength gets smaller. So you just should know that. And we said that there are varieties of the slowing down of the speed depending on the material. Typically for solids, most solids, it's about 1.5 in the visible range. But it can vary, and we'll get into that, I keep saying, as we go into more depth onto just what's going on here. Then we had an explanation of Snell's law, which depended on the fact that although we're talking about rays, and here are the rays is the direction that between, say, perpendicular to the crests, which someone asked, what is these wave crests or wave fronts is another word that's used here. The ray is perpendicular to that. It's the direction in which the wave is traveling rather than the direction along the crests, okay? And we can derive that on wave properties. Now, then we had the idea of total internal reflection, and I also talked about polarization by reflection. Now, we had a little office hour before this, and I could see that, and it's reasonable to be a little bit mixed between those two things because there are a lot of things that are similar and yet they're different. So let me just quickly sort out what we're talking about here because there's a lot of similarities, but they are different. One is, which one came first? The critical angle, which is sometimes called TIR, total internal reflection. And the words mean very well said. It's total, meaning it's complete. Internal, meaning that if I have a solid material, internal to that, the light is totally reflected. So the words say exactly what it is, which means that normally you would expect that when light meets a boundary, some of it is reflected, sure, but some of it should refract and go out into the second medium. in this case, let's call this medium 1 because that's from which it's coming. And this let's call medium 2. What it turns out is that at a certain critical angle, is this in the way for some of you? At a certain critical angle, the angle of refraction is 90 degrees. So there's where a 90-degree story enters, there, between the normal and the refracted beam. So let me maybe show that. See, the refracted beam would go 90 degrees. If the angle gets any greater than that, this thing wants to bend more than 90 degrees, which means bend more than 90 degrees, which means it stays inside the material. So from here on out, the light cannot get out. See, when light comes straight along the normal, it gets out perfectly fine. Some gets reflected, actually, of course, but it can get out. But when it's beyond the critical angle, the angle of refraction is 90 degrees. So that's one thing. It has to do with refraction, and there is a 90-degree story in here. Now the confusion comes in, so this is total reflection. Then we have the other idea of the polarization angle, or Brewster angle. And here the story is a little bit different. Here we're talking about a reflection at a surface. The light comes in, and the light refracts, and the light reflects. This should have been the same angle. Let me revise this one to make the angle of reflection equal, as best I can draw it. So theta in, theta reflected here, equal, right? Okay, so that part is good. Now there's another 90 degrees in here, but that's this 90 degree. There's a 90-degree angle here. So you want to keep, these are two different stories. The idea here is that you come in with unpolarized light. And somebody in the office hour had this very good image, namely of the bristle brush, the bottle brush with all the bristles sticking out in every direction. That's what comes in this way. It's got all the polarization directions in principle, and they all come in. When you come out here, it's taken a haircut. Oh, there's another image of these guys that have their hair cut like this with a tomahawk. What do they call that? Tomahawk? What is it called? Mohawk. Mohawk, yeah. It should be tomahawk, as far as I'm concerned. But it's a mohawk, and it's been mohawked in this direction. Yeah, that's what happened. The bristle brush has been mohawked, and you end up with one direction. The reason is because of this 90-degree angle here, the wave, it's vibrating the medium, and the vibrations that are vibrating this way, because this direction of reflection is at 90 degrees, it's along the axis of these vibrators, the material, and this does not radiate in that direction. It only radiates in this direction. These guys radiate in this direction, and so you end up with polarization like that. So you want to be clear on these 2 points. It's a different phenomenon. This gives you a polarization. There is a 90-degree story in here. There's a 90-degree story in here, but it's a different story. And, oh, the other thing we could run through is that they both are susceptible to Snell's law, which governs refraction, which is, okay, let me write Snell's law once for all up here. N1 is the medium you start with. N1 sine theta 1 equals N2 sine theta 2. So all you do is you apply that law, but interesting things happen because of this 90-degree angle, and you're going to have a sine of theta, and a sine of 90 is 1 and you're going to get another, you're going to build in another story when you have this angle being 90 degrees. So for example, in this case here, we're saying, what angle would I have to come in with to make this refracted angle 90 degrees? That's the question. So I would write Snell's law as I come in from medium 1, N1, let me start a little higher, N1 sine theta 1 equals N2 sine theta 2. But theta 2 is 90 degrees. Isn't that nice? Theta 2 is 90 degrees. So sine of theta 2 is 1. So I just put in Snell's law. Sine theta 2 is 1. So I get N1 sine theta 1 equals N2. And so that's at this critical angle in particular. So I have sine theta of the critical angle is equal to N2 over N1. Now sines must be less than 1. So it says that N2 must be less than N1. So you can only get this when N2 is less dense than N1, because then the light coming to the surface bends away. And what you're trying to do is get it to bend 90 degrees to the normal. So it can only happen when you're going from a dense to a less dense medium. That's all. It's just very simple. And this is the thing you'll find in the book. All you're doing is taking advantage of the fact that at the critical angle, the refracted beam is now parallel to the surface, and beyond that, it doesn't get out. So here we do a similar thing, taking advantage of this 90 degree in this story. So we do Snell's law again. N1 sine theta 1 equals N2, let me abbreviate, sine theta 2. Okay, so here our first medium, say, is this one. And our second medium is this one. So, okay, I have sine theta. At the Brewster angle, you'll have N2 sine of theta 2. Now we use the idea that this angle must be 90 degrees at this point. So we want to build this. See, I want to try to get what is theta, the incident angle. I'd rather not have it involve theta 2. I really want to know what angle shall I send the light in order to get it polarized coming out. So I'm really trying to get everything to have only theta incident in my formula. So I'm trying to get rid of theta 2. But I can get rid of it because I know that this is theta 1, this is 90, this is theta 2. So the sum of these three is 180 degrees. So I can write that theta 1 plus 90 plus theta 2 is 180. Isn't that nice? All right, so I take off 90 from here, I get 90. So I'm trying to get everything in terms of theta 1. So I can say theta 2 is 90 minus theta 1, right? And you can recognize that. Okay, let me draw a little triangle here. If I have theta 1, this is a right triangle with angle theta 1, 90 minus theta 1 is this, right? Because this is 90. So, and the whole sum is 180. So this one is theta 1, or 90 minus theta 1, right? Which is, okay. So, and if I want to take the sine of theta 2, the sine of 90, the sine of that is this over the hypotenuse. That's the sine of 90 minus theta 1, but that's also the cosine of theta 1. So the sine of, this is all trigonometry that we dearly love, sine of 90 minus theta 1 is the cosine of theta 1. That's sort of the cosine of the complement. You know, you remember these vague rules, but you can just derive it. So what we get here, finally, let me write it over here, is that we have n2 sine, no, let me do n1 sine of theta of the Brewster angle is equal to n2 cosine. See, there was the sine of 90 minus the Brewster angle, so it's now the cosine of theta Brewster. So the Brewster angle occurs when you have sine. Now I'm going to bring all the Brewster angle things on one side, cosine theta Brewster, and I get n2 over n1. And the sine over the cosine, we remember from trig, is tangent of theta b. So that's the formula for the Brewster angle. And we've just nicely used the fact that those two rays are at 90 degrees from each other because of the mechanism of radiation by these dipoles driven in the material. Now, it's interesting that the Brewster angle, can you get polarization when n2 and n1 are greater, when this is greater or less than 1? In other words, you can get it off when this medium is more dense or less dense and more dense. In other words, would you get it coming this way too? Could you? And the answer is yes. There's no real reason, because the tangent doesn't have any limit. The tangent can be as much as infinity. So you could get polarization when you go, if you have a medium from light air to a solid, you can get polarization at some angle. Interesting. And on the other hand, you could also get it when you're going this way inside the medium, but it'll be at a different angle. In other words, it's interesting, I don't know which angle is bigger. We can easily figure out which. When n2 is larger, when it's bigger than 1, it's more than 45 degrees. And when n2 is less than n1, tangent of theta is less than 1, so it's less than 45 degrees. But it could happen either way, which is sort of unlike this phenomenon here. I just pass that on to you. So don't get them confused. They're two different phenomena. There is a 90-degree thingy in one and a 90-degree thingy in the other. But they're doing, well, it's a little, and deep down it's the same phenomenon. It's how the dipoles are vibrating. But here it's glaring that the dipoles simply don't radiate the polarization in this direction. So you're only left with that polarization. Okay, so I hope that helps a little bit. Yes, ma'am? It's totally the same. Well, oh, actually, in some sense, it's the same. We're using the word polarization in some different senses. I don't know which senses you're using it, asking about. But we do have the idea that if you put an electric field on a material, you polarize it. That's one polarization. Here we're talking about something different. Here I have an electromagnetic wave, which is composed of electric and magnetic fields. And I'm choosing the direction of the electric field, and I'm calling that the polarization direction of this electromagnetic field. So they are different. We use polarization an awful lot, I'm sorry to say.
But when we were talking about waves, like the lab that we did a week or two ago,
Yes?
we were putting waves through slits.
Yes.
Showing that there were particular directions.
That's right.
That would be isolated. But here, are we going, is it the same thing, or are we going to unpolarize things?
That's right. Then we're talking about the polarization of light, and we're talking about the fact that the light has, the E fields have a particular plane of vibration, and if the polarizer is its polarization direction in line with that, the light, we call that polarization direction of the polarizer. That's the direction of radiation vibration that passes through. Does that answer your question?
It's not entirely clear to me how this thing angles is polarized.
This thing here.
All we're doing is changing what material you're coming from.
Yes. Why does it change? Why does it polarize the light? That's a very good point, and I try to explain it in the following way. The thing comes in unpolarized, like that bristle brush with every different direction. It hits the surface. The surface reacts to that light because it's made of electrons and protons and stuff. So it starts vibrating. And those vibrations radiate. It's like an antenna. The atoms in the material are driven antennas. But the key thing about the vibration, this is a very deep question you're asking. I tried to answer it a few times, but it's hard to grasp. If you have vibration up and down an antenna, the antenna radiates to the side. It does not radiate in that direction. You have to get it, you have to get a component of acceleration in the direction you're trying to radiate. It does not radiate in this direction. That was something I showed when I had this long antenna. I try to go to the end of it, and it doesn't radiate this way. It's just the way dipole fields are. They go like this, and there's nothing along the axis radiated. So if I'm the material here, and a light beam comes along this way, granted the material here is being vibrated by all those polarizations. It's also a bristle brush in here. But what does it radiate? What do these guys radiate? The ones that are vibrating this way radiate in all directions sideways, like this. So they're radiating this way, the ones that are going here. So they are radiating the new reflected wave. The ones that are polarized this way, you see my thumb is pointing in that direction. It doesn't radiate in that direction. So there is no polarization like this. Get that? That's a deep reason behind the polarization effect. My thumb is, because they're vibrating this way, no radiation comes this way. So I end up, this polarization is radiated this way, so I get this polarization. This one is radiating this way. It's radiating sideways, sort of like this, but it's not radiating in that direction. A slit, just a simple slit. Yes, a slit alone won't do it. A slit alone, what you have to, well, a polarizing screen has a preferential direction because there are molecules in here. Well, a single slit won't do it. We did have a grill of things. Yeah, a grill. If you have enough of them, they will block the waves that are trying to get through and they're vibrating this way. They'll be creating currents up and down those grill wires, and it sort of use up the field. So that's why you have to turn the grill sideways, so when it vibrates, it doesn't give you as much current sideways. But so this is the passing direction because it doesn't use up the field. So that is a polarizing direction. Say again there. Well, yes, it's slightly different mechanism. Yeah, actually, it's pretty much the same mechanism. When I'm doing this, these are acting as picking up antennae. So if my field is going like this, these antennae are picking up the field, and then they're reducing the field behind them because they've caught some of the waves, and some of those waves are driving the electrons up and down, using up some of the wave's energy, so that the wave doesn't get through the grill if the wires are this way. These are properly aligned antennae. If you want to pick up the wave, you want your antenna this way. But it will block the wave. It uses it up because you've taken something from it. If you have enough of them, it'll stop the wave entirely. It's a very good point. I mean, it's not easy to grasp the first time through, but so it's good. Now, yes, sir. It's perpendicular to the reflected direction. Yes, that's a very, I haven't defined that very well, but what we usually do, if you have an incident beam coming in, we do some, should have a pencil, or a pen. If you have an incident beam coming in and a reflected beam going out, we define this as the plane of incidence. In other words, if I have a ray coming in, it'll bounce off in the same plane. So that's the plane of incidence. Yeah, and here is my surface, right? So now I have polarizations in all directions like this coming in. And on my way out, I only have polarizations this way because the medium can't project polarizations that way. So this is what's called the plane of polarization. Got that? Yes, sir. It's partially polarized, partially, because you sucked out some of the energy from one of the polarizations. So it's partially polarized. Pardon me? Means that you won't have as many guys vibrating this, a stronger field vibrating this way as that way. It's just, that would say that the electric field, the strength of the field is given by the magnitude of the field. But so you'll have, in the bristle brush analogy, you'll have taller bristles in one direction than the other. So that it's partially polarized. Of an unpolarized wave, all the bristles would have the same length around the, you see my image of the bristle brush? So they would all have the same length, they'd all have the same strength. On the other hand, if it's partially polarized, then it might be elliptical, namely you have more strength in that direction than that. So that would be partially polarized because there's more electric field strength in that direction than in that, because some of it has been radiated out. Okay, let me move ahead because there's some little fun things, and I also wanted to get to relativity today. Oh, I don't think I'm going to make it again. But anyhow, I want you to see these demos. So in any case, the story is that this subject is not as complicated as it might seem because we treat mirrors and lenses with the same formula. You just have to know what they mean. You have the situation, I think you've already maybe experienced it in the lab, where you put an object in front of a lens or a mirror, and then some light passes on that object, the optical element, and creates a new image. And this formula tells you where these relative images are with respect to what's called the focal length, f. Now the only really tricky part of this is that these s's, the distances, and the f have numerical signs, plus and minus. And it's a heck of a job, unless you've got a very good memory, to remember all the different possible cases of when it's one s positive, one is s prime negative, one is f negative. So I'll tell you a very quick, simple way of remembering it. I'll just erase this, may I? What I would say is set up the most obvious case. And though the most obvious case, everything is positive. And if it isn't the obvious case, then the thing is negative. The most obvious case, if you have a lens, when you think of a lens, you think of that. In fact, the word lens is the same word that comes from lentil. You know, you ever seen lentils? They're shaped like that. So you can think of a thing as lenticular, like a lentil. So here's a lentil. And so that's, I mean, most people, if you say lens, they don't think this. They think this. So think the most obvious thing. And the most obvious situation is that you have an object in front, a person, a thing, and that you have an image behind. If you have that, everything is positive. If you have anything more peculiar than that, then it's negative. For example, if in this case, for some reason, so this is the object, and that was the image, and that is our, I'd like to call it the standard case. And everything is positive. Plus, this is positive, this is positive, this is positive. Everything's positive, no problem. Okay, if it should turn out that you have this situation, and you have your object, and it should turn out that your image is over here, that's negative. It's not the standard case. Object in front, lens over here, image over here. This guy is in the wrong place, he's negative. Yeah. Also, if suddenly you should see a lens that doesn't look like a lentil, it's negative. So if I see something like this, I say, that's not my standard case. This is negative. Its F will be negative. This is providing me an S, F, and S prime. If they're in that order and it's a lentil, they're all positive. If you see something like this, an object and a non-lentil and an image, this guy would be negative. This guy would be positive because he's in the normal position. And it'll turn out that with a thing like this, you'll never get an image over here. You'll always get an image over here. You'll always get an image over here. So that'll be negative also because he's in the wrong place. That's all you have to remember. Same is true with mirrors. When you think of a mirror, what do you think of? Well, I think something like this, frankly. Right? Shiny surface over here. Actually, the more natural would be a plane mirror, like the mirror in your bathroom. But if you were to think of a curved mirror, that's what I would think of first off. And if everything, and then the standard case is the object over here, the image over here on this side of the mirror, and that's all positive. Object, image, shape here, that's all positive. So you have S, S prime, and F, all positive in the standard case. If anything is different from that, for example, it could happen that S prime is over here. If it should turn out that you're suddenly getting an S prime on the other side of the mirror, that's negative. That's what you have to remember. Just remember the standard case, and if anything comes out wrong, peculiar, it's the wrong sign, the opposite sign. Or you could have a mirror that looks like this, so-called convex mirror. Here, it's not like that, so this would be a negative mirror. And it always will create an image on this side. No, it'll always create an image on this side. So that'll be negative too. Your object is, typically your object will be outside the mirror because otherwise something's going to break if you go inside the mirror. Unless you're Alice in Wonderland or something. So that's it. That's all you have to remember. To remember the standard case, yes?
So the object, I guess S is always positive?
Actually, it doesn't have to be. You can get some cases where the object is behind a lens because it's coming from somewhere else. We'll get to that maybe with optical instruments where you're having compound lenses. So typically, in a normal case, the object is in front of the lens or the mirror. But you could have yet another object over here, a lens of some sort, which creates an image over here, and that is the object for another lens. So, and that'll be behind this, and it'll be negative for this one. So that is conceivable. But in a single lens, you can always set it up so that the object is in front of the lens. That we'll leave that for compound things like microscopes. That's yet tomorrow, next week's chapter. Okay, now the importance of focal points I try to emphasize, and the only thing that you really have to know is the distances S and S prime are adjustable. You can put the thing anywhere you like. The one thing that is determined by the geometry of the optical element is its focal length. And there are two different formulas which actually turn out to be rather similar, in fact, to each other. for the focal length of a lens. It's given by this. Again, there are some tricky points here. The only tricky point, though, is that you have to, these have signs. As you might expect, and I could show it to you, the focal length is given by n minus 1, 1 over r1 minus 1 over r2. And again, the r's have signs. But again, we just go with a simple convention. If it's convex toward the object, we give that a positive sign. If it's convex away from the object, in other words, this material like this, and you have your r like r2, say, if it's convex away from the object, we give that a negative sign. So again, it's kind of the simplest, most obvious thing is called positive, and the less obvious is called negative. So that's it. That's all you have to remember. Okay, and I think I put this in here. There's a simple rule. The standard case of both the lenses and mirrors are those. And the focal length, it turns out, of a spherical mirror is simply half the radius of that surface, which I talked about, I think, last time. And there are different kinds of mirrors. You have, of course, the plane mirror, like your bathroom mirror. You have the concave mirror, which ladies may know as a makeup mirror, and the guys know as shaving mirrors, where you are concave mirrors, and if you get close enough, you will see yourself magnified. Then you have a convex mirror, which is the lower one, which is the mirror familiar to you. It's your side view mirror in your car. The side view mirror of your car is that kind of a mirror because what you're trying to do is see a wide angle, and you always want to see the things right side up. It would be very distracting if you looked in the mirror and suddenly you saw things inverted, you know, like so and also you want to have a broad view. So it turns out that the side view mirror is a convex mirror, and it reduces the size of things, but at least it keeps them upright, which is a blessing. Now, the way we solve problems is by knowing certain special lines with respect to these optical elements. You know, this is really a rather longer story than I was hoping to get into. Well, we just have to do it, though. The point is that there are special lines, and if you know 3 lines, in fact, if you know 2 lines, you can get a point. So you can find out where things focus. For example, we know if you have a lens like this, if you send a ray through the center of the lens is pretty much plate glass, right? It's not angled. So the light will go through straight. So that's one nice line. Then we have, if you send in a light parallel but not through the center, that light will refract toward, and when it comes here, it'll refract away, and it will bend, and it'll pass through the focal point at the focal length. So a parallel beam goes through the focal point, and that's enough to determine where the focal point is. You could do some others. Let's see, what would we do? Well, you can do one down here, of course. It's the same story. It will pass through here. A parallel beam will pass through the focal point, or a light passing through the focal point, if I can get that angle right. Oh, yeah. Will go parallel. So I should do that one with a different color, perhaps. Again, it's the same idea. The light is reversible. If it passes through the focal point, it'll go parallel. If it goes parallel, it'll pass through the focal point. So depending on what rays you have available to you, if you have 2 or 3 of them, 2 is enough, you can locate the image. And we have the idea of magnification. The relative height of the image over the object will be the relative height, relative distances with a minus sign. Again, the signs come in because it's possible for the image to be inverted. The thing I did want to show you before the time runs out is this idea of real and virtual images. You can talk about them, but it's really fun to see exactly what they are. And for example, here's a demonstration. I don't know what you can see. Do you see a lamp glowing? Okay, and it looks like it's over here. Everybody agree? Abracadabra, hocus pocus, mocus hocus. Ta-da! Hocus pocus. What's going on here? It's just smoke and mirrors. This actually is oh, it's glass. It reflects somewhat, so it's a mirror. Actually, the lamp is over here. And the light is coming, and it's spreading out, because it's coming this way, and it's spreading out to you, and it looks like it's coming from here. Isn't that unbelievable? So I can put it back in or not, as you wish. I can put it over here, and the light goes on. So that's a virtual image, because it looks like it's coming from here, but there's no light here. So this is a virtual image. Can you see it even far over there? Okay. So that's a cute one. Now, on your way out, we have only 5 minutes. Please do stop and see this one. This is a little bit different. I should maybe explain it a little bit. What it is this is one of these concave mirrors, which let's do the geometry of the sky. It's maybe worthwhile. Yes. Okay. So the picture here is I have this giant mirror here. It has a radius about yay. Okay. So it has a focal point about here. If I put an object at the focal point, and I use my formula, 1 over s plus 1 over s prime equals 1 over f, which is the formula that applies to lenses and mirrors. If I put the, let's see, I may want to put this at the, let's see, when would I get an image, this image, I want the image magnification to be 1. Because I want, see what's going on here, some of you have seen this already, there's a bunch of false flowers hanging from here. And I want an image of that, same size, to appear here. So I want it to be inverted and the same size. So let me see what I have to do here. I want the magnification to be 1. I want the bunch of flowers to be reproduced, but right side up. So there's actually real flowers here, and I want them to appear here. So magnification is 1, and that's s prime minus over s. I want that to be 1, so I have to get s equal to s prime. That has to be 1. So I have 1 over s, that's the object distance, plus 1 over s prime, that's 2 of them, equal to 1 over f. So I have to make s equal to 2f, which is the radius of the sphere. So what I should do is put the bunch of flowers at the radius of the sphere. Here's my flowers. And in principle, the light will come from this point. It will reflect, and I'll get light even something like this. So the parallel beam will pass through F. You see, so all the light from this point, see, here's my 2 rays. Here's my 2 special rays, one of which, hits here. Oh, that's another special ray, because it hits perpendicular, the radius like this. The angle of incidence is equal to the angle of reflection. So a special ray will come.
Sorry.
That's all right. Welcome. So that's one set of rays. The other one is the one that's going parallel to the mirror. It'll pass through the focal point. So all the rays coming from, and every one in between, will end up at this focal point. So a point on this flower will end up as an image here. And the rays, in fact, continue out. So in other words, they're coming in all directions. And they will all come out, and they'll all come out. So this acts like as though the same way this does. So that's a real image, because all the light is coming out of that point, just like it's coming out of this point. That's a real image, because the light actually started here and is going out. So that's a real image. You could project it on a screen, because the light is coming out of that point, or it's going to hit that point. So let me turn this guy off. Oh, it's fun. OK, so time is, it's up. So that's the theory of this. And it's quite a striking illusion. If you haven't already seen it, please do. And then you'll come and be amazed that that's exactly what's happening here.